Hi everyone, we continue with designing catalytic reactors. This is just introduction on what are reactors involved in CHE505. So for the introduction of different types of reactors to be involved in CHE505, we'll be looking at the packed bed reactor. Previously, you have been introduced to packed bed reactor, but I think the only reactor that have been introduced is this one. The reactor filled with a bed of catalyst. But in industry, there are other types of packed bed reactors, which is multi-tube reactor and also single tube reactor. So the Z term here indicating the height of the bed of the catalyst. So for starting, the Z is 0 and L indicate the height, how much height is the bed of the catalyst. Let's look at the mole balance or design equation for packed bed reactor. So first thing is that we have to assume there's no mixing in which that the fluid in the packed bed reactor flows from one point to another point with no mixing. Therefore, for single reaction, we can assume that this is the design equation. This is the design equation, which is velocity times the differential of concentration over differential of height bed of catalyst equals to the kinematic velocity of one species times the reaction rate. For multiple reactions, this is the design equation, in which the same velocity times the differential concentration divided by the differential of height of the catalyst bed equals to the summation of the kinematic velocity of multiple reaction Ij times of the rate of reaction for the main one. Now, in order to calculate the total reactor volume, the total reactor volume here, for example, you have to consider the volume of the fluid basically referring to the feed that going into the reactor. Let's see that this stream it goes to the reactor and it's going to fill the reactor over here, plus volume that is participated by the catalyst. So this is so-called the volume that is filled by the catalyst in the reactor, in which that the volume fluid is regarded as void fraction times volume of reactor, and volume of catalyst can be regarded as 1 minus void times volume of reactor. Okay, now we look at the slurry reactor and fluidized bed reactor. Previously, for packed bed reactor, we have in packed bed reactor, the catalyst is fixed. There's no stirring, there's no mixing. Tapi kalau reactor that has mixing and stirring, kita panggil dia sama ada slurry reactor or fluidized. So kenapa dia slurry? We call it slurry if the fluid is in liquid form. And we called it fluidized bed if the fluid is in gas form. So the design equation, we take it from the model of a CSTR, since there is mixing, there is stirring happen. So kita ambil model CSTR last time, in which CA0 minus A. So again, A is referring to limiting reactant. Dan kalau nak kira residence time, tau it's the same as volume of fluid divided by viscosity, kinematic velocity, and it is the same as epsilon of volume reactor over kinematic velocity. Epsilon, we called it as epsilon. So epsilon meaning the void in the reactor. Okay, so this is an example of the slurry reactor. This is an example of fluidized bed reactor. Another type of reactor is riser reactor. In this type of reactor, the catalyst inside here will be going through a high flowing fluid. Therefore, because of the high flow of fluid, the catalyst will be out from this reactor, and that's why a cyclone is installed here in order to trap the catalyst in this cyclone, and the catalyst will be cycled back to the reactor. So the other name of this riser reactor, we can call it as plug flow tubular reactor. So the design equation for riser reactor, we can take it from packed bed reactor. This is the design equation or the mole balance. It's the same as the packed bed reactor. So apart from finding the volume of reactor, and also apart from being introduced the design equation for each of reactor previously been introduced to you, like riser reactor, slurry fluidized reactor, and also packed bed reactor. And one more parameter that you need to design or you need to calculate is the reaction rate. So since in this course we have to consider the reactor and also the catalyst inside the reactor, so we have to design the reaction rate taking into account the catalytic activity. So first, the assumption is you need to assume that the catalyst in solid phase, and the reactants is either in gas or liquid phase, and the reactions occurs on the surface of the catalyst, so means there is no reaction happens in the fluid phase. Therefore, in order to calculate the overall reaction rate, or the other name is pseudo-homogeneous rate, we have to take into account the area of the catalyst, surface area of the catalyst divided by volume of reactor times the reaction rate of surface catalyst, the reaction rates that happens on the surface of the catalyst. Okay, now in order for you to calculate the area over volume parameter, the area over volume over here, kita mengambil contoh packed bed reactor, in which the packed bed reactor filled with pellets of catalyst, and so the pellets of catalyst kita boleh kira menggunakan surface area of the catalyst times density of the catalyst. Therefore, theory, area over volume also be the same as surface of the catalyst times density of the catalyst times volume of catalyst divided by volume of reactor. Sebelum ni kita dah cerita volume of reactor as volume of fluid time plus volume of catalyst, right? And volume of catalyst is the same as 1 minus epsilon times volume of reactor. So kalau you simplify, you will get this term. So area over volume for packed bed reactor is the same as surface of catalyst surface area times density times 1 minus epsilon. So another parameter that you need to find in order to design catalytic reactor is the what you call this space-time. So basically space-time is defined by volume of fluid in reactor divided by volumetric flow or kinematic velocity as I said before. Tapi sekarang kita ada, last time we learn on how to find space-times on the homogeneous reactor. Kita tak ambil kira pasal different phases. So kalau kita tak ambil different phases, kita assume semua satu phase. So it is volume of reactor divided by volumetric flow. Tapi kalau kita ambil different phases in the reactor, which is heterogeneous, so kita have to take into account the epsilon over here. Okay, tau is equals to epsilon of volumetric of volume of reactor divided by volumetric.